Dear students, welcome to our class on demonstration of thermal conduction. Fourier's law for thermal conduction. Very interesting. Here is the source of energy. The energy is conveyed through radiation without the presence of the medium in between the flame and the container. In the container there is water here. You are seeing the water here. Once the energy is conveyed through convection, the energy is transferred from one molecule to other molecules. Then within the medium itself, without the movement of the molecules, conduction into my right hand is taking place. Now, of course, evaporation is going on. Without the presence of the medium, radiation. With the actual movement of the molecules, convection with the water. Without the movement of the molecules in the medium, conduction and evaporation. So, this is how the process. Another small example is when I am keeping this iron rod and putting energy at point A here. Now, this is the point B. From point A to point B, from where there is a heat, high heat to low heat, it moves. Now, this is what we call it as the conduction without the movement of the molecules in the medium. Now, as far as the Fourier's law of heat conduction Q is concerned, presume that this is the a plane surface. This is a plane surface. A plane wall A. Temperature on one side T1, the other side is T2. T1 is greater than T2. T1 here passing through. dx is the thickness. Q is the energy. Now K is the thermal conductivity, watts per meter per degree Kelvin. Now T1 is greater than T2. What is the dt here? T1 is greater than T2. T1 minus T2 is dt. Now Q is proportional to A. What is A here? The area actually perpendicular. Area. Now Q is proportional to A. Q is proportional to dt by dx. dt is T1 minus T2. dx is the thickness. Now Q is equal minus K. This is very interesting. Here I had explained minus K A. Minus K A. dt by dx. dt dx. dt this one. dx is this one. So thermal conductivity K. Q is the heat conductivity. Now in watts. This is all in watts. Now what is thermal conductivity K? Q into D. T into A into T1 minus T2 or delta T. Joules per second per meter per degree Kelvin. Now thermal diffusivity alpha K by rho Cp. K means thermal conductivity, density and specific heat of the substance. Now here I would like to tell you, I would like to impress upon you that Fourier's law of thermal conduction states that the rate of please note that the rate of heat transfer is directly proportional to the area normal to the direction of the heat flow. Normal to the direction of heat flow and temperature gradient T1 minus T2. Now here there are two differences, main differences between the thermal conductivity and thermal diffusivity. There are two similarities. First, there are two differences. Now similarities are both are measures of heat transfer. Both are given in time rates. Now, what are the differences? The major difference is thermal diffusivity alpha K by rho Cp cannot be determined without thermal conductivity. In other words, thermal conductivity by heat capacity is the thermal diffusivity. Now, thermal conductivity is the flow of heat. Thermal diffusivity is the spread of the heat. I am standing on the floor. If floor is cool and air is hot, from my hot air to cold floor, heat flows. That's what we call the conduction. Now, two differences, major differences between thermal conductivity, thermal diffusivity are, we want usually high thermal conducting, less thermal storage appliances. So whatever the energy you convey, it is used. Say for example, you are preparing an item for food. Okay, that's what. Whatever heat we give, it should be used. Thermal diffusivity. As far as diffusivity is concerned, there also two uses are there. Where we don't want more heat to enter, we go for thermocol. Thermal diffusivity is less for that. Where we want more heat to flow, we want more thermal diffusive element to allow flow more heat so that it spreads. So this is what I would like to share with you. Thanking you for your patient hearing.